Let's create a DFA for this language W, where W starts with a 0 and has odd length, or starts with a 1 and has even length. So looking at this problem, this one's a little bit more complex than the other ones I've covered so far. But what we're looking for here is essentially, if we have an input string, let's say it's a bunch of zeros and ones as defined by our alphabet here. So we have 0, 1, 1, 0, 1, 0. This string starts with a 0, so we're looking for an odd length. What is our length? 1, 2, 3, 4, 5, 6. That's an even length, so therefore this is not valid. If we add another character onto the end to make this a length 7, well, now this is accepting. Same thing can be said for if we start with a 1 and have an even length. So if we have an input string, if we have 1, just putting a bunch of random characters here. So we start with a 1, so that means we're looking for an even length. 1, 2, 3, 4, 5, 6. That's an even length, so we're going to accept. If we have a 0 at the end, well, that's no good. We're going to actually reject this because the length is now odd. So that's kind of what we're looking for here. Now, something that might be really intuitive to start with is, say we have our initial state, we'll call this state 1. We split off into two kind of tracks. So you'll notice here we're detecting if we start with a 0 or we start with a 1. And then we check for a different thing based on if we start with a 0 or a 1. So that kind of translates to splitting off into two different tracks. We'll call this the starts with a 0 track going up here, and then the starts with a 1 track going down here. So now let's create some new states. So now essentially on each of these paths here, we want to check if it's even or odd. And what we can do for that is, say we're just checking if, say our language is just W is odd length. So if we're just looking for W has an odd length, we can have a transition from state 1 to state 2 on any symbol. And to get from state 1 to state 2, we need exactly one character to consume. We need either a 0 or a 1. Now, if we create a transition to go back, what we need is another character to go back to state 1. And then we're going to go back and forth and back and forth. So from state 1 to state 2, we need one character. From state 2 to state 1, again, we need 2 characters. And then from state 1 to state 2, now we can have 3 characters. And then do you see what's happening here? We're counting on state 1. The length is odd, even if we're on state 1. If we're on state 2, the length is odd. So that's how we kind of count with the DFA if our string has an even length or an odd length. So we can do something like this for every path. So what we can do is we'll call this state 2. We can go on state 2 on any character 0 or 1 to a new state. We'll call this state 3. And then on state 3, we can go back, and then we can just keep going back and forth like this on every character. Now, since in this diagram I put up here before we started at the very beginning with no characters, which is an even amount. However, we're starting with already a 0 consumed, which is an odd length. So state 2 is going to be our odd state, and then state 3 is going to be our even state. Now, if we start with a 0, what length do we want? We want an odd length. So therefore, we want to accept on state 2. And then we can do something very similar for the 1 path. So if we start with a 1, we're looking for an even length. Let's create our kind of algorithm here to detect even or odd length really quick. So let's call this state 4 and state 5. So if we start with a 1, state 4 is our odd state because we already consumed one character, which is an odd number to be here. Now, if we go from state 4 to state 5, that's 2 characters we've consumed, which is an even number, and then we'll go back and forth, so on and so on. So state 5 is going to be our even state. If we're on state 5, that means we have an even length. If we're on state 4, that means we have an odd length. So we're looking for an even length here. So therefore, state 5 is going to be our accept state. So this is the most intuitive way to think about this problem, and although this works, this technically works for the language, there's a very clever way to reduce this to 3 states. If you want to challenge yourself, maybe pause this video and see if you can do it yourself. But I don't think many people would get this on their first try. So let's kind of forget about this diagram for now. Let's create a new diagram to explain this concept better, because it is pretty difficult to understand at first. So say we have an initial state. We'll call this state 1 as always. And then we have like a transition on 0 and we have a transition on 1 to new states. If we transition from state 1 to a new state, states x and y per se, that means we have a length of 1. Now, if we go down the 0 path, are we going to accept on state x with a length of 1? Well, if we look at our language here, if we start with the 0, we need an odd length. So yes, we do want to accept. A length of 1 is odd, so let's accept. Now, if we go down the 1 path, say we have an input string that looks like just 1, so we follow the 1 arrow to state y, do we want to accept? Well, no, because if we start with the 1, we must have an even length. If we're at state y, we have an odd length, a length of 1. But what we can do is, remember how we were doing our flip-flops here, where we're going back and forth to determine the even or odd? If we have another transition on anything, we're going to want to go to an accept state, correct? This is going to want to accept. But what if we just route it to the accept state we already created? So we route it to state x instead. So now we're accepting if we have another character on 0, 1, let's say. And then if we have another character, so say this would be like if we had, so now we have like 1, 0. So we go from state 1 to state y, and then that's on the number 1. And then on our 0, we go from state y to state x, and we accept because it starts with a 1 and it's even. But then if we have an input string that's like 1, 0, 1, well then now when we read this 1 and we're on state x, we want to go back. So we go back on 0, 1, and then we don't accept because it's an odd length. It's kind of clever how you can do that. But does this work for, remember we're kind of neglecting the 0 path here. Does it work for the 0 path as well? Well, let's see. So let's feed it in an input string that starts with 0. Let's say we have 0, 1, 0. Does this meet our requirements? So we need to start with 0 and have an odd length. So that is supposed to accept. Now let's start with a 0 and have an even length, which is not supposed to accept. Let's see what happens. So when we're testing for this here, we're going to start with the 0. So we're going to go from state 1 to state x. And then we're going to consume this 1 to go from state x to state y. And then the 0 to go back from state y to state x. And this works. We accept and we're supposed to accept. So that's good. And now if we're doing this second language here where we're not supposed to accept, let's test it. So we have a 0 at first. So we go from state 1 to state x. Then we have a 1, so we go from state x to state y. And then we have a 0, so we go from state y to state x. And then we have another 0, so we go from state x to state y. And this is not an accept state, so we're going to reject, which is what we want. Now, this is very clever, and you might get it after looking at this for maybe 10, 20 minutes and being like, oh, wow, this finally makes sense. Even though this is much more intuitive, as a computer scientist, we want to optimize and get something more like this, because the more we can optimize, the less states we have, the less space we're taking up in diagrams and algorithms, and it makes things more efficient overall. It requires less computing power. So how do we modify our original diagram to fit this new kind of concept we created? Well, let's essentially route on 1. We're going to route all the way to state 3 instead of going through this separate kind of path here. And this is a less nice way of looking at it, but it's essentially doing the same thing. When we encounter a 1, we're going to go to a non-accept state. But if we encounter a 0 at first, we're going to go to an accept state. This is because 0 wants an odd length and 1 wants an even length. So upon length 1, aka reading the first character, we're going to accept if it's 0, or we're going to reject if it's 1. And then we're going to flip-flop back and forth based on where you started, and it works out like that. A much more human readable way to write this would be to first we're going to move state 3 down here. So we're going to transition on 1 to state 3, and then we can move our kind of flip-flopping transitions like this. This is a lot more human readable. It's probably much nicer to look at. So yeah, this is the DFA for this very complex language here. I believe on this channel, this is the first kind of problem where it's like you have to think a lot about how to optimize it. But first, let's check if we have the entire alphabet coming out of every state. So do we have a 0 and a 1 coming out of every state? Out of state 1, we have a 0, 1 arrow. And then state 2, we have a 0 and a 1 arrow. And then state 3, we have a 0 and a 1 arrow. Perfect. Now, feel free to test this for as many test cases as you'd like. Yeah, but this is the DFA for the language. I hope this made sense. I know this was complex and I tried to explain it the best, but I hope it made sense, and best of luck with whatever you're using this knowledge for. Thank you for watching.